rule. Okay, so let's go to the second slide. This is literally the only thing you have to remember. Treat these as if they're variables. Treat them as if they're variables. And what I mean is this. I'll give you an example. If I had, this is going to sound trivial, and I agree that it is. 2a plus 3a is how many a's? But can I do this? Can I combine them? No, right? I just can't do it. So as a result, when I'm looking at a problem like this, I realize that I cannot combine things that are not like terms. So when you're thinking about like terms, treat whatever is under the radical as if it's the variable. Again, treat something under the radical as if it's a variable. For example, 2 root 7 plus 3 root 7 is 5 root 7s. I use the exact same rule as I do with variables that are like terms. So if I had another setup that looks similar to that, but instead I have 2 root 7, but now it says plus 3 root 6. 3 root 6. Are these like variables? Not like variables, not like terms. So I cannot combine these values. Sure, you can come up with an approximate decimal and add those numbers together and get an approximate answer. You can. But this is the exact solution at this point. There is no simplified form of this. That's the entire lesson today. Now, obviously, I'm giving a simple example, and you're going to be like, oh, homework's just on a chart, which I agree. They're much harder than this. This is really easy. But the rule is no different for every single problem you're going to do. You have to then model it to use it on more difficult problems, such as cube roots and fourth roots and stuff like that. So we're going to do today just 6 examples, okay? ABC for number 1 and ABC for number 2. So we'll start to get more difficult as we go through. So we start with a pretty easy one like part A. By the way, 6.1 and 6.2, you have questions? Some of the things I might be going over. So if you're not sure, stop me, even though I know you want to go after school. If you don't get what I'm saying and I'm doing this, you're going to be lost in this also. So there's something I do that you're confused about, ask me. Eduardo.
Just to go back to that. So the radical.
So the first one, clearly root 48 and root 75 cannot be combined. Does everybody agree with that to start? Yeah, we can all see that? Please do not just add those two numbers together. You can't do it. Again, you cannot add things together if it's not the same radicand. The number or expression under the radical. As a result, I must simplify first. And that's an obvious thing. If you can't go any further, that means you must simplify individually. What do I break root 48 into? Root 48.
16 and 4.
16 and, careful. Help them out. 16 and 3. You're on the right track. Good. So the 16 becomes a 4 root 3. I agree with that. How about the 75? Valentina? Good. And what we're going to notice, just like in section 5.4 and 5.5, it's not a coincidence that both radicals have a 3 on them, right? It's got to work out that way for these kinds of problems to be simplified, or else the problem wouldn't be asked. So you're going to see on like standardized tests that when this happens and you need to simplify an expression, it will work out nicely, just like the factoring problems in 5.4 and 5.5. The quiz that you guys took was an example of that. A lot of the things that factor then cancel either vertically or cross-canceling. Same idea here. So this becomes 9 root 3. And I cannot go further because root 3 cannot be simplified. Root 3 is in its simplest form. There's no denominator, so I don't have to go with any of the rationalization stuff because there's no denominator in this problem. And root 3 can't be broken down further, so I stopped there. Questions on part A? A is the easiest one, obviously, we're going to do. Okay, so let's go to part B. Part B is a little bit trickier, but it's not terrible. Helen's got her hand up right away. Good, Helen. What do you want me to break 16 into with cube roots, Helen? Agreed. Cube root of 8 happens to be a perfect cube. That's why she chose that. So that's what she starts with. And then you got the other one? Yeah, 27 and 2. And Helen picked up on it right away that the 2 under the radical is occurring in both terms again. It's not a coincidence that this happens. The idea is that the only way to subtract or add things is if you have the same radicand, so there's a good chance that whatever's left over will be the same in both cases. Well, this is 5 times 2 times the cube root of 2 minus 3 times the cube root of 2. That's 10. I'm doing the steps. I know you wouldn't write all these out. I'm just doing it. Okay, so just watch the simplification and make sense of it. 5 by 2. Those are both on the outside. The common mistake I see is that students take the 5 right here and they multiply it by both of these things. First of all, you can't multiply something on the outside into the inside unless you were to actually square it first. You could do that. But this term here is multiplied by one thing. There's no plus sign. You're not distributing. So please don't multiply that 5 by both things there. Outsides multiply outsides. Insides can multiply insides. That's how I remember that one. That was from section 6.2. Outsides multiply outsides. Insides multiply insides. Questions on part B. On part B. You got to know your cube roots also, by the way. If you don't know them, you're going to be really behind on the test and you're going to run out of time. If you sit there and rely on your calculator, it's not going to work out well for you. Okay, you know your cube roots. Know, like, honestly, 1 through 5 you got to know. After that, it's not as important. But 1 through 5 you should absolutely know. Part C. Root 50 over 3 and root 2 over 3. Plus or minus? Plus, okay. What do you think for this kind of a problem I should do? And there's not only one right answer, by the way. So you can take different approaches for a problem like this for sure. Thumbs up?
Yeah. Can you, since they both have the same denominator, and they're both square fractions, can you combine them together like what we do for 3?
Can't, unfortunately, no. Because remember, you can only multiply insides by insides or multiply outsides by outsides. The only time you combine with addition is if what's under the radical is identical. So it would have to be root 2 over 3 and root 2 over 3, and then that would be 2 root 2 over 3. What do you think I should do? What do you think I should do? I mean, I see 50. 50 like rings a bell. It's like blaring, right? 50, look at me, hey. What do I do at 50? Gina?
Can you break it down?
Yeah, so start with that. What does that break into?
5 and 5.
So in this case, 50, not 5 and 5.
25 and 2.
25 and 2, which becomes 5 root 2. In a minute, we'll do that, yeah? So this gives me 5 root 2 over root 3 plus root 2 over root 3. And I broke up the root. I don't have to, but I'm just doing it to do it. What do you notice, though, right now at this point? What do you now notice? You got 5, ready? 5 of these plus another of these. Use common sense. And I got 5 of something plus one more of that same something. What I must have more?
6.
Yeah, I gotta have 6 of them. So this is where it gets a little bit tricky because students forget that they can add these two things together. The 5 on the outside is just like a coefficient, right? Isn't that what we're doing? Isn't there really a 1 outside of here? So it's really like 5x plus 1x is 6x. So it's 6 times this. Now I'm not done. I'm not saying I'm done, but that's what I have right now. It's 6 times this quantity. Yeah, 5 of them plus 1 of them is 6 of them. But I can't leave a radical in the denominator. Can't leave a radical in the denominator. Eduardo, I see a root 3 here, right? I don't want a root 3. I want something that's a perfect square. So what can I multiply root 3 by to make it a perfect square?
By 3.
Yeah. Let's take, and we'll say root 3. Let's multiply it by that. Very good. And if I do it to the bottom, I've got to do it to the top also. I'm going to do it to the bottom. So the bottom, though, nicely becomes 3 times 3, which is root 9, or simply 3 in the bottom. That works out. Up top, I'm left with 6 root 6. Again, this is over root 9. And I'm going to show the steps. I know you wouldn't really do it this much. Or you wouldn't show every single step, is what I'm saying. So take a look at the work as we progress through. 1 second, Mark. I got a root 2 times a root 3. Inside multiplied by inside, which makes that a root 6. The 6 out here Please, please, please. This 6 is over 1, so I can easily move it up to the numerator. Don't let this confuse you. This is 6 over 1. Root 3 by root 3 gives me root 9, which is going to give me 3. Yeah, Morgan.
When you add 5, you added those ones with the parentheses. How come on the bottom you didn't have 2, the cube, 2 times the square root of 3?
How come I didn't put a 2 here is what you're saying, right? At the end, like down there?
Yeah.
Well, think about fractions. If I had 5 1/4 and another 1/4, how many 1/4 do I have?
6.
You have 6 1/4, not 6 1/8, right? Did you double the denominator there? So why would you do it here? You see what I'm saying?
Yeah.
It's kind of like you have to get your mind around, but treat these things as if they're variables. You wouldn't alter the variable if it was 5a plus 1a, it would be 6a. It wouldn't be 6 over 2a or something like that. You know what I mean?
Yeah.
So don't just add in the rules because it seems like, oh, I should probably do that. Think of them the right way. And another thing to think about again is that you could have written it like this. You could have written your fractions and your radicals like that. And if you like doing it this way, that's fine. But it's still the same answer, 6 and then root 2/3. So it'd be 6 with a root around the whole thing. It's no different than what we had. Okay? It's no different. Let's try the last 3 together. So these ones are just going to get a little trickier. That's all that's happening here. And it looks really complex, but it's not, I promise you. And by the way, this is a cube root here. It's not 5 cubed. It's 5 times a cube root. I should put parentheses there. Okay, and same thing for you, please, people. As it is already, I got to be honest, some of your handwritings are scary. So with that said, on the test, really make it clear if something is an index or if it's a power. That 3 there should be an index, so I should have put those parentheses I just added in. 5 is on the outside there. It's 5 times the cube root of that whole thing. Let's start with the first one up top. 5 root 48 minus some other mess. Right? That whole mess on the right. Well, 5 root 48 can be broken down nicely. 48? What's 48? 16. Good. 16 by 3. That's right. So we'll start with that. Then becomes 5 times 4 times root 3, which is 20 root 3. See what I'm doing? I'm kind of just simplifying as I go. Make life easier on you. Okay? Instead of going through every part, I'm just like, you know what? Let me just keep simplifying this. Now, the last part, I recognize right away that it looks like I have a coefficient outside of a binomial. Right? Do you see that? It's a coefficient outside of a binomial. What should I do with that coefficient if it's outside of a binomial? Distribute it to both. So be careful here. Outsides multiply outsides. Insides multiply insides. So when I distribute this to the first thing, the 4 times the 3 multiply each other, which gives me 12. And then the 6 times the 2 on the inside multiply each other, which also gives me 12. Now I can do one of 2 things. I can put a big parenthesis here, and then later on use that negative, or I could associate the negative right now. I'm going to recognize that there's a negative on the outside that I'm distributing, so I'm going to put it on the outside, and I'll carry this negative down for now, and then I'll do the double negative in a minute. It doesn't matter which way you want to do it. So let's carry that negative down. And then I have to, and I'm going to erase it at the top. I'll erase the colors. I clearly can't erase colors right now for some reason, all right? So instead, what I'll do is I'll use yellow. We're going to take this 4 radical 6, and we're going to distribute it in here. So this 4 radical 6 becomes 4 times 5. Those are on the outside. Okay, in case you're not sure what I'm talking about, I'll point. That 4 right there times that 5 right there gives us a 20. And then on the inside, I've got the square root of 6 times the square root of 3. It's going to give me the square root of 18. And now I just have to go through the process of simplification. If something doesn't simplify, don't worry about it, but go as far as you can for everything. So the second one I'm going to write as 12 times root 4 times root 3. Now this is going to be a double negative, so I'm going to switch this to a positive at this point. And that'll be 20 times root 9 times root 2. Again, I'm just breaking this up. This 12 becomes 4 by 3. This 18 becomes 9 by 2. It's clear that these are like radicals but this is not going to be able to be combined because that's root 2. These are root 3s. The root 3s will be able to merge together, but the root 2s will not. So this becomes 12 times root 4, and that's really 12 times 2, which is 24 root 3. And at the end, this is going to be 20 times 3, which is 60, and that root 2 carries down. So I've got 20 root 3 minus 24 root 3 is negative 4 root 3 plus 60 root 2. Okay, if you're not sure what I'm doing, please ask. Please ask, okay? I'm just literally multiplying these two things here and these two things here to give me the next terms. And then I recognize that these are like terms. Okay? 12 times 2 is 24. 20 times 3 is 60. These are common terms or like terms. I can say 20 minus 24 is negative 4. Carry down whatever the rat hand is. Part A. Part A. Take a minute to digest it. Ask me questions. I'm happy to go on to Part B, but I just want to see that we're all good on Part A first. Gina, do you have a question? Which part, Regina? Go from one step at a time.
Like the first part, I get.
So that's good? Everything here?
Yeah. No, that's the part I don't get. Like,
Right here?
Yeah.
So this part you don't get. So if I look at this, this is 4 root 6, right? And when I multiply 4 root 6 times 3 root 2, I have to multiply the outside pieces. That's why I circled them in blue. See, the 4 times the 3 gives me the 12 there. And then the 6 on the inside times the 2 on the inside gives me the 12 on the inside. But then I have to recognize that this is really a coefficient, and this was a binomial in the beginning. So I have to distribute it now to this thing also. So this 4 again multiplies by this 5, which gives me the 20. This root 6 times root 3 gives me root 18 right here. I carried down this negative here because I did not apply this negative yet. I left that negative on the outside. Once I'm inside of here, I have to break down the 12 into 4 and 3, which is here and here. Take the 18, break it into 9 and 2, which is here and here. And then I saw this was a negative, so I applied it to this by making that negative, and then I took negative, negative, and made that a positive right there.
Okay. That was like the first part was the one part I did.
Okay, good. Guys, ask, please, if there's any part you don't understand, ask. I want to definitely go over it, make sure you get it. A lot of this is like following logic. It really is just one process after the other. So what really helps when it comes to a thing that is repetitive? Who plays a sport here? Who plays a sport? You're constantly throwing a baseball, right, in a game. What might you want to do outside of the game? Practice throwing that baseball. So these are the kind of topics that I know some of you are like, oh, yeah, I get it, no big deal. 5, 4, and 5, 5. I feel like a couple of you thought you're like, oh, I'm just factoring and canceling, no big deal. But the quiz results weren't like the best of the year, to be honest. We need to practice. We need to make sure we're practicing timely as well. So don't wait 2 or 3 nights to do your homework. Do it that night. Okay, so for this kind of a topic, practice is huge. How about part B? Let's see. I'm going to copy it down a little bit lower here. Part B says 4x times the square root of x cubed minus the square root of x to the 5th. Now, I'm not going to lead you astray, most likely. I'm not going to set up a problem that doesn't work. So although this looks complicated at first glance, it's pretty important to recognize that it's probably not that bad if you actually just break it down. So we need perfect squares. We need perfect squares. So 4x, nothing happens to it. But I got to break this up into something, and I got to break this up into something. The question is, what's the perfect square and what's the not perfect square, Regina?
Would it be x squared and x?
Good. And over here?
X squared and x cubed.
Careful. I could take on more than x squared. Remember, it's got to be an even exponent.
Oh, x to the 4th.
Good. Yeah, and the idea, again, is that I'm going to be left behind with radical x. And aren't those the same? So this is like a common term or a like term. If you're left with a radical x here, which you're going to be, and you're left with a radical x here, that's nice. So if you had done x squared and left with x cubed, you wouldn't have been able to combine like terms, and you'd have to realize you could break up x cubed further, and you could have done that also. So this becomes 4x times absolute value x times root x minus x squared times root x And then the absolute value doesn't actually matter because I'm going to do 4x times that, so it's going to be squared anyway. So it doesn't matter at all. And take a look at this. It's 4x squared root x minus 1x squared root x. Always put the number 1 when there's no number there. So what's your answer going to be? What's your answer going to be?
3x squared root x.
Very good. Again, it's 4 of these minus 1 of these. That's how I think about it. You need to mentally picture it the way I just drew it. There are 4 of these quantities or these factors, and then there's 1 of this factor. 4 of them minus 1 of them is 3 of them, and I carry them down below. Regina?
Where'd you get the absolute value from?
From right here. I can go over that with you after school. We went over it in class the other day. Okay? Square root of x squared is always absolute value of x. I'm happy to go over it again, though. Okay? For now, just remember that. But I'll go over it with you after school. It's fine. Or whatever. Part C. Part C. We have 2 times the cube root of y to the 4th over 3 plus 5 times the quantity. And this is going to be cube root of, watch what I'm going to do right off the bat. I'm going to break this up right off the bat. Cube root of 2y to the 4th over cube root of 54. Okay, I'm going to start right away as writing it that way instead. I like to write my radicals as separate parts when there's a quotient inside of them. You can leave it, it's up to you to decide. At this point, though, now I can say, let me find my perfect cubes. Perfect cubes. Perfect cubes, not squares. So what's the perfect cube that comes out of y to the 4th? Out of y to the 4th, Ellen? Very good. So y to the 3rd times y. Okay, and she's already saying, you know what, this is going to become 2y times the cube root of y over 3, and I agree. It's a good way to start it. So she's pretty much breaking up the 4th into the 3rd and the 1st. The cube root of the 3rd is the 1st, actually, right? And then this 1st carries down over here. On the right-hand side, or the right-hand part of the sum, what do you got?
Well, the 2y sort of becomes the same. 2y to the 4th is, you can take out the y to the 3rd, or it would be y to the 3rd, y just y. And then the 2 would be another.
I'm going to put a 2 there also for now, just for now, because it's not a perfect cube. Go ahead, in the bottom.
20 cube square root 27 times 2.
Very good. And so the reason I left the 2 behind is because I can do this now, which is nice, right?
Yes.
Okay, so take a look at what I did there. That's a nice technique. If you're ever left with the same factor in the top and bottom, oh, this should not be y to the 4th. This should be y. Sorry, right there, that should be y. So if you're never left with the same factor in the top and bottom, definitely cancel, okay? Don't try to rationalize that. And that's y again. I'll correct that right now. Okay, there we go. So this should have been a y right here. So now what we're ending up with, if we simplify further, is a 5 here still. This becomes y over 3 times the cube root of y. And I know that looks kind of funny, but it is right. Okay, you can put the root y, or the cube root of y over 1 if you want to. That's fine also. So if I simplify things and make them look nicer, this is still 2 cube root, 2y cube root y all over 3 plus 5y cube root y all over 3. I can do that. Why did I do that? Because now, look, think of this as a thing and think of this as a thing. I've got 2 of those things plus 5 of those things. As a result, I have 7 of them total. And I can put a parenthesis if I want. I don't need it. Okay, you don't need the parentheses here. I'm putting it there just for now, just to be safe. Okay, but again, this is the common term in both that you can then add together. And it carries out, think of this as 2a plus 5a is 7a. So a lot of this is literally just being very, very meticulous with your work, right? Seriously, that's all it's about. You have to be careful along the way. You have to take the right cubes out. or fourths out, or third, or squares. Whatever the radical is, you have to look for the perfect form of that. Get the perfect form of that and simplify. There's homework for this. We did go a little slow because I kind of really wanted to get through this well, so we didn't have time for that. But please, tonight, practice your problem sets. Those are due tomorrow. This homework will be due on Wednesday then, right? As always, the problem set's always due the day before. This will be due Wednesday. You could take a look at this if you wanted for a minute, but we literally have a minute of class left.